So first of all, hello everyone. My name is Gonçalo Nogueira. Thank you all for coming. So I finished my master thesis in 2016 in Instituto Superior Técnico. After that, I stayed a couple of months extra researching with Professor Jorge Fernandes from IST. And after that, I started working in 2017 in Socionext in England. With all the work I've been developing, I've decided to come here and present to you state-of-the-art. And today my presentation is called State-of-the-Art FinFET Technology, and I'm going to give you an industry designer's perspective, namely my perspective on this subject. So what you're expecting to find in this presentation is first an introduction to pointer technology, pointer stimulus technology, and its limitations, why the need to use these recent technologies. Also, after this, I'm going to speak about the FinFET transistor and how to design with this transistor. First of all, I'd just like to say that this presentation is divided in two halves. So in the first half, I'll be speaking about this. Then I'll have a round of questions, a little break. And after this, I'm going to advance on to the second half, where I'll present the advantages of FinFET comparatively to pointer transistors. Then about the challenges of working with this kind of technology, and last but not least, definitely the potential future of solid-state circuits. So let's start. Everyone probably knows this graph over here, Moore's law. Moore predicted many years ago that every 2 years the number of transistors in a chip would double. Well, this trend has been seen to happen. Actually, up to more or less recent years, it has been decaying, but maybe it will catch up, maybe it won't. Anyway, the thing is that a long time ago it was predicted that scaling transistors for digital applications would decrease the power and increase the speed of these transistors. So people started looking into the potential of this scaling. And this created a market demand for faster, smaller, and less power-consuming circuits, which inevitably led onto the need for transistor scaling research. So let's look onto the pointer bulk CMOS. So here you have a CMOS transistor. Got your drain, source, the length here between drain. The length is defined by the distance between drain and source. Here you've got the channel region. As you scale this transistor, the drain and source start becoming closer and closer. This presents some issues. But first, let's look at the digital operation of the circuit. So how does this operate? When you have this works as a switch. When you have the gate voltage high, drain and source are supposed to be shorted. When the gate voltage is low, they're supposed to be open circuits, no current flowing around here. But this is where the first limitation of the pointer transistor comes. As you scale the length, you start, although they might be close together, you start having currents flowing through the substrate. And this is one of the limitations. The second limitation is caused by an effect called drain-induced barrier lowering, which causes threshold voltage variation. Although you see this defined as a fast transition, well, it's supposed to be, you have this defined here. You have a transition between this point here and this point here. With the reduction, with the scaling of the transistor sizes, the drain starts to enter and into the channel region, which changes the carriers inside and the amount of carriers inside, and messes up with the threshold voltage of the transistor. So this is stronger, the effect is stronger the closer they are together and the higher the drain voltage is comparatively to the source. So I'd like to show you here what one of the effect of leakage. Here what you see is dynamic power density. is the power consumed by the circuit in operation, what it is used to consume normally. But this started getting in the way, which is the power consumed by leakage. And for smaller nodes, you see that the leakage power starts to catch up with the dynamic power density. This is a huge limitation, and this needs to be overcome. As such, recent technologies were developed to tackle these issues. One of them is fully depleted silicon on insulator. So let's have a small look onto the planar CMOS. Here what you see is an insulator, silicon oxide, and the idea was to isolate this region from the substrate. So a thin body layer, a thin body of silicon oxide was deposited beneath the channel, the source, and the drain. Still, there was another idea which came to mind, which was the FinFET. So we passed from having this planar section to rising up everything, and this is not the best way to show it, but you've got the gate around the channel area. So how does it look like, the structure of a FinFET? Looks like this. So here you've got the source, the drain, and the gate. The source and the drain constitute a fin of the transistor. You've got the silicon oxides, and underneath you've got the body, or the P substrate. Here you have the views, front view, top view, and side view of the transistor. The part that you see on yellow here is also insulated to separate the gate from the channel region. So let me see if I can show you something. So I've developed a model of 3D transistors online, which you can all access and look onto it later on if you want to. Let me check if I can show, sorry, here. So it seems like I'm having some troubles displaying this. Okay. So here you go. So I've developed this. It's in a website called Tinkercad. If you want to go and visit, just look for FinFET. And I've developed the 3D model of the FinFET transistor, which you can just explore and go around and look if you want to understand better how it looks like. So now returning to the presentation, let's continue. So don't forget, inside here you've got the channel. This is still an NPN transistor, or PNP. So for instance, the S and the D, the source and drain, it's N, and inside it's P. So how does a structure with multiple fins look like? Looks like this. You just copy paste the fins and you put them on the side. For those of you who enjoy layout or are interested on how this looks like on 3D in layout, for instance, doing a transistor with multiple fins, you have a metal, which you put a metal layer which connects all the sources, all these fins, and on this side also you connect all the fins for the drain. Only after this is that you put a via which goes onto the first layer of metal. Now, I also want to show you this slide so that you can more or less understand on a 3D way how does it look like, everything together. So let's move on to more interesting stuff, transistor design. How do you calculate the width and the length of these transistors? So the length is just here, the length of the gate. But I'd like to know if anyone in the audience knows how to calculate the width of a transistor like this. Does anyone have any idea? Okay, let me show you then. This yellow part, it's the effective width of the channel. So it's calculated this way. It's the width of the fin plus 2 times the height of the fin. So it's that perimeter. The width only has discrete values, so you can only attribute discrete values for your width, equal to the number of fins or the number of multiples that you are using in the design. As per the length, you have technologies which have single size transistors. You only have one length and one width, and you have to use transistors just with that size. Or you have technologies which have multiple size intervals. For instance, on more advanced nodes, you might find also that the allowed length sizes are, for instance, 20 nanometers, 40, 60, 80, and then you have an interval between 100 and 150, which you can choose any length, 102 nanometers, 103, etc. Now, how do you, for these technologies which just have a single transistor, which have just one single size for the transistor, how do you tackle with these, with the design? So first of all, to increase the width, you stack transistors in parallel. So in schematic, it looks more or less like this, while in layout or 3D view, it will look more or less like this. You can imagine, for instance, grabbing here all the fins and merging them all together. This way, the combined width will be all of this. As for the length, you stack the transistors in series if you want to increase the length. So it will look in schematic more or less like this. And then in 3D layout, it will look more or less like this. So you can imagine, for instance, grabbing all the gates and pushing them all together. This way you'll have a transistor with length of 3L. Or for instance, imagine here grabbing the yellow parts and bringing them together. Now, when you're talking about FinFET, you're talking about advanced nodes. You have FinFET for FinFET processes for very small length. So you start having short channel effects. You have threshold voltage variation, although it helps the FinFET with these effects. It's still there, just less strong. And with the Dibble effect, the drain-induced barrier lowering, you have that as you decrease the length of the transistor, the threshold voltage varies. Also, with the VDS, if you increase the VDS of the transistor, the threshold voltage will also decrease. This is also one of the behaviors. And for very short channels, you also have carrier velocity saturation. So I'm sure that all of you here know this equation, which also stands for a FinFET transistor. But it's related to the velocity of the carriers in the channel times the charge in the channel. The thing is, for that small size, you have very strong electrical fields, and this causes the velocity of the carriers to saturate, changing the behavior of the transistor. And you start having a linear dependence on VGS minus threshold instead of a quadratic dependence. I still remember when I saw this the first time, I couldn't believe it. I thought that the models were wrong. But later I learned. So I want to alarm you regarding transistor design, how to overcome these limitations. So let's go through the usual analog design flow. You first have your circuit that you want to achieve a certain gain, achieve a certain bandwidth, and then you develop the circuit model. Okay, I'm going to do a differential pair, then I'm going to put here cascodes, etc. Then you define the GM and the GDS for each transistor. And then one of the usual ways that people who come out of the university, I speak for myself, deal with sizing the transistors is you use end estimation. Use formulas like this to try and get the behavior of the circuits. But then you look at the technology parameters. Okay, new n, use a new n of the technology. Use a threshold voltage of the technology. But when you're varying W, when you're varying L, when you're varying even VDS, you're the current is varying significantly. So when in the end, after you put everything together and you've done your end estimations, you go and verify it and the circuit does not match what you wanted at all. Instead, I propose you this, GM over ID simulations. Here, what you do is you plot the curves of the transistor, the parameters to check how does the technology behave. You define operating points for each transistor, you size and you verify. For instance, let me give you an example of something that happened with me in my company. Even with 7 nanometers, I designed amplifier. I designed a circuit with 20 to 30 nodes, and I used this methodology. I defined operating points for each transistor, I planned everything, I set everything down, I put the circuit on cadence, and I simulated. And no node was 10 millivolts off of what I had planned. For me, this was magic. So what I want for you to have in mind is that this could be a better starting point for you. So let's dive into it. What is GM over ID methodology? It's a graphical methodology that uses graphics of the behavior of the technology for you to define, for you to build your circuits. So how does this work? First, you define circuit specs. Then you plot transistor parameters versus GM over ID. You select operating points for each transistor, and then you build the circuit. That's all you need to do. But also let me give you what is a feeling of what GM over ID represents. GM over ID is called transconductance efficiency, and it gives you the GM that you can take out of a transistor for the amount of current that you pass through it. So for saturation region, for VGS higher than the threshold voltage, you have this. You have the GM over ID is equal to 2 dividing by VGS minus the threshold voltage, which is also called as the overdrive voltage for those who haven't heard about it. Also, I would like to show you something. Even when the transistor has VGS smaller than the threshold voltage, is still conducting current. The thing is that it conducts so little current that you just despise it and you consider the transistor to be off. But it has an exponential variation with the VGS, the current. So this region where the VGS is smaller than the threshold voltage is called subthreshold region. And in this region you have that the GDM over ID is equal to 1 dividing by an n factor times the thermal voltage. This for planar CMOS, usually it's around 28 volts minus 1. And just to give you here, for completeness, here you got the thermal voltage, which is given by some constants, and the factor n is given by this, with CD, the depletion capacitance of the transistor. So here, this is what I propose for you to use to test and to check how does the technology behave. You have, wait, I'm sorry. You have here, you put a voltage source to control the VGS, and you put a voltage source to control the VDS, and you just plot the transistor parameters. You sweep VGS and you check how does it behave. Here, with this graph, I want to give you also a little bit more understanding on GM over ID. So for ideal behavior of saturation region, you've got this formula, and you've got this behavior of the circuit, this red line. It's supposed to behave like this, and then it's supposed to explode for VGS equals to the threshold voltage. As per the subthreshold region, you have a constant 28 here. But if you grab your transistor and you test it in a lab, you check that the real behavior is the green line. Also, I wanted to just give you a little bit more information on this. So it's said that a transistor is in strong inversion when VGS is higher than the threshold voltage. It's in weak inversion when it's much smaller than the threshold voltage, and moderate inversion when it's more or less, around the threshold voltage. So what do you do? You have your transistor, you have this down, and what do you do to check to build your circuits? You check, you plot transistors, the transistors parameters versus GMID. So which ones would you usually do? For instance, I would use the current, the intrinsic gain of the transistor, GM over GD, the Rout, the gate capacitance, transition frequency to see the speed of the transistor, normalized current to compare between transistors of the technology, and whichever you find important for your design. So my suggestions when using this methodology are the following. First of all, plot the transistor parameters on the x-axis and the GM over ID in the y-axis. And also plot each curve for different VDS values in the graph. If you're trying to understand the technology, if you don't understand it, or if you have difficulties understanding what are the behaviors with the change in width or length, I suggest you to also plot each curve for different width and length values. But for me, that I believe that I already have sensibility for that, I just go for the VDS. And it should look more or less like this. I'm not sure this is completely visible, but there are here multiple lines. That is for multiple VDS values. And here I've got Rout in logarithmic scale, and here GM over ID. So what do? Okay, I want the transistor to have more or less this Rout, and I know that the VDS, the output should be around 0.35 VDS. That's what I'm planning for my circuit. Come here, go up. Okay, I know it's in this operating point. I take out the GM over ID. I check the current. Okay, or the current flowing through, or the gain, or with this GM over ID, I get to know the other operating points of the transistor, the other parameters. Sorry. So lastly, just as a suggestion, start from the hardest transistors and size them towards the easiest. So when you have your circuit, you have to achieve the specs that you're given. But some specs are hardest to achieve than others. So imagine, for instance, in this circuit. So here, I've got 2 stages. So anyone here can tell me which 2 stages are these? Okay. Let me go through. So this stage here is a common source, and here you've got a source follower. And in this circuit, if you want to achieve gain, you know that the only transistor that gives the gain to the circuits, or the most relevant to the circuit, it's this transistor. So if you're trying to achieve a high gain with this circuit, I would suggest starting on sizing this transistor, and only then moving on to the next ones, which are easiest to size. So for now, I would just like to do a small break and see if anyone here has any questions. Need to catch some breath. So I'd like to ask the audience, does anyone have any questions?
Yes, I have one. When you do this GM over ID testing simulation, you use the models that are that are being delivered by the function.
Yes.
That's correct?
Yeah, when I use the...
What I mean is, do you use some kind of HEV type of approach model, or do you just use
So if I understood your question correctly, you're asking me if I use the model, the PDK models for the GM over ID. Yes, I do use the models from the PDK for the GM over ID, I believe, because I don't do any optimization. I just see the transistors, see the relations, and try to get them onto the operating point that I need to. I'm not trying to optimize, I'm just trying to achieve the specs, mostly. Yes. So does anyone else have any questions?
Regarding
Yes.
Anything suggested adding them in series. So adding in series actually, you have three transistors in cascade, so it's not exactly the same as adding channel lines.
So if I understand your question correctly, you're asking if they behave like cascades, being in series. No, actually they don't, because they all have the same gate voltage.
Yes, but they have different VGSs depending on the operating.
Yes, they do have different VGSs, but if you try and check that on Cadence or on any other PDK, any other software, you'll notice that the behavior starts to become like a transistor with 2L, 3L. I believe that if you try to stack 10 or 20, the behavior won't be like a transistor with 10L or 20L. But if you stack at least 4, 5, 6, still kind of safe.
I'm thinking about the dynamic response, because each one of those nodes is going to add an extra volt to your circuit. So you have an amplifier, you use transistors like that, you are, instead of having 1 or 2 volts, you're having 3 times the number of volts. So from a stability point of view, it becomes more complex. I think from a DC point of view, it kind of behaves like increasing 3 times the channel length. But my question is more from a dynamic point of view, because then you have 3 or 2 new nodes to the circuit, and each one of those nodes has a parasitic capacitance, which is the CGS, and it has a GM associated with it. So,
Well, first of all, in order for those poles to be, for the poles in the chain of, in the series chain of transistors to be relevant, first of all, that needs to be the dominant pole or one of the relevant poles of the circuit. Second, for high-speed applications at least, I don't believe that the people use increased length or to use the or stack them in series, because the increasing the length reduces the dynamic power or the dynamic performance of the transistor. So I believe that never comes as a limitation. Sorry?
it's a technique that we only use for low frequencies.
Yes, for low speeds. Yes, definitely. Does anyone else have any question? Okay, so I'll proceed on to the next bit. So on the second half, I'm bringing you first the advantages of the FinFETs regarding comparatively to the planar transistors. So first, let's revisit these transistors and try to understand what are the main differences between them. Here, you've got a planar, and you can notice that the gate is only on one surface of the channel. Here, instead, you can see that the gate is almost surrounded by the channel is almost surrounded by the gate. It has 3 surfaces around the channel. So this means that the FinFET has a better voltage, better gate control over the channel. Also, you move from a 2D transistor onto a 3D transistor. Why? Here, you only see length and width. Here you see length, width, and also height. So you start entering into the 3D realm of transistors. So let's revisit two of the main disadvantages of using planar. One of them is leakage. So like I told you, as you start approaching source and drain, you've got leakage flowing through the substrate. In FinFET, this doesn't happen. Well, it happens, but the effect is quite insignificant. Just you have a small current passing possibly here through the substrates on the bottom part. You have also a stable threshold voltage. You probably remember the Dibble effect. The Dibble effect would said that as you start approaching these two transistors and as you increase the drain voltage, that the carriers start to protrude into the channel and they reduce the threshold voltage. Here, this doesn't happen because you have because the gate is surrounding the channel more and it's controlling the channel and doesn't let the drain enter into the channel region as much. One of the consequences of FinFETs is smaller body effect. Body effect comes from the voltage, the voltage of the body, the substrate affecting the channel, and here the channel is just in contact with the substrate. While here, although you have a smaller body effect because the voltage of the substrate might affect the bottom part of the channel, but it won't affect the top part. This can be seen as an advantage for people that are trying to achieve linearity. You do a cascade of FinFETs and you have no body effect. This helps with linearity, but it can be seen as a disadvantage for those people that like to use the body effect for calibrating transistors. Now, another advantage of the FinFET comparatively to the pointer, it's higher device density. So here you see a device with 3 fins. Now, how do you think a planar device like this would look like? You would need to grab these yellow parts and then fold them and bring them together. And you'll see that the width of a planar device with the same width as the FinFET would require a larger area to be there. So therefore the FinFET has a higher device density. Also, due to the reduced Debye effect, the Debye effect degrades the GDS performance severely. And as the FinFET doesn't have a pronounced Debye effect, it ends up having a smaller GDS and therefore a higher intrinsic gain. Another advantage is that you have a higher jam over ID. This is caused by the reduced depletion capacitance in the FinFET transistors. You almost have no depletion capacitance. In the planar technology, you have depletion capacitance which is comparable to the oxide capacitance. Also, they are faster than FDSOI and planar, and they have a better gate matching. Here you can see FinFETs with a smaller AVT. So the gate matching comes from the fact that these channels are undoped, which increases the matching of transistors. So the FinFETs are easier to scale, but this is not the advantage by itself. The advantage is a consequence of the scaling, which is the way the power, the current, everything scales in circuits. So I want to visit with you digital scaling theory. Actually, I do digital scaling theory. So when you're scaling transistors, you scale horizontal and vertical dimensions by a factor of alpha. You reduce the threshold voltage and supply voltage by a factor of alpha, and you increase all doping levels by alpha. As a consequence, the current in a scaled device decreases by a factor of alpha, and also all capacitances are scaled by a factor of alpha. The delay time over an inverter it's also decreased by alpha, and you end up having also the power decreased by 1 to the cube. Still, there is something missing to this formula, which would make a better comparison. Can anyone guess what is it missing here for the scaled power? So you're making the circuit smaller. Therefore, you need to check the power for constant area. Must not forget, this that you see here would be for the scaling of a single device, but you want to know how does it look like as you scale the power for the same area, and what you get is this. Also, I'd like for you to try and guess what you think are the major applications of this kind of transistors. Where do you think they are mostly applied? Can anyone give me a guess? Don't be shy. No? Okay. So I'll tell you. We've got processing circuits. This is one of its main applications. It's smaller. It has, it's used mainly for digital. You can see that from the advantages it brings. It's used in computers, wearables, data centers, supercomputers, AI, and deep learning. Also, as they are very, very fast, they are used for networking, namely for 5G and for the physical layer of the internet. Now, on to the challenges. Why is it hard to design and do layout with FinFET? First of all, although I just showed you that the currents go down, the customers want the speed to go up and the specs to get better. So you end up having higher current density. This causes self-heating. This is caused by power dissipation on the channel. And the main reason why you have self-heating is also because you have poor thermal conductivity. The heat stays all inside the channel due to the insulator. Usually the heat flows through the substrate down, but here the heat has nowhere to flow. So it ends up being trapped here in the channel. This per se alone is not the issue. There's also things to contribute to the issue, which is electromigration. Both of these together are the issue. So let's dive onto electromigration. For those of you who don't know about this, in real circuits, you have the transistors on a layout, and then you have wires connecting them. Actually, a circuit is like a cake. It has a multiple layer cake. So you have the transistors at the bottom, and then you have multiple layers of metal to drive signals from one place to the other. And these lines, these metal lines, are more or less like this. So throughout the lifetime of the circuit, you have current flowing through the metals, and once in a while you have an electron that hits on an atom and dislodges the atom from its place, causing either voids or helix. And they look more or less like this. When you wonder why your circuits, why your phones stop working, this could be one of the causes. Maybe not the software, maybe it's this. The performance of your circuit is being degraded by this, and also electromigration also causes failures in circuits. This is used as a reliability measure to check the aging of circuits, to check on the lifetime. And you've got this formula called the mean time to failure. It's an empirical formula which gives you, like it stated, the mean time for the circuit to fail. Now, the important part for you to take out of this is that the mean time to failure is proportional to the exponential of the inverse of the temperature. What does this mean? Temperature goes up, the mean time to failure goes exponentially down. So these together with the self-heating effect degrades, it's a headache for designers using high-speed applications, designing for high-speed applications. Also, another thing that you have is high metal resistance. So this is a line of metal, like those that you have connecting transistors in your circuit. And you've got the resistivity, the resistance of this metal is given by the resistivity times the length dividing by the width and the height. So what happens when you scale down the dimensions? Can anyone tell me? Can anyone have a guess? Do you think it's going up, going down? Up, down? Yep, it's going up. Exactly, it goes up by a factor of alpha. Now you scale up down to 7 nanometers, and then you start having very large values for the metal resistance. This causes higher drops. Like I told you, a circuit is like a multiple layer cake, and the supplies usually are on the top, and the supplies need to be driven down to the bottom. So they flow through a lot of metal layers. And one of the consequences that you might have, for instance, is this one. you're trying to supply, to design an amplifier, and your routing of the layout as high resistance here and parasitic resistance here and here. These would degrade the performance of your amplifier. As for this circuit, it's an R2R ladder. You have, for instance, a voltage. You've got here a parasitic resistance in between this node and this point and this point, this point and this point, between the switches and the resistors here. By the way, I'm representing this as a resistor. And like I told you, this can degrade the performance of the circuits. Also, as the circuits become smaller, the clients want the circuits to go faster and faster. But there's one limitation. These metal lines, they behave like RC lines. So you've got resistance, capacitance, resistance, capacitance, resistance, capacitance, and so on. And the resistance goes up. As for the capacitance, I prefer not to speak about it because it's a very complicated behavior when you scale it, because you've got also multiple kinds of capacitances. But as for the resistance doesn't help in this case. For you to have more or less of a taste, so for FinFET nodes, you have vias going for, above 20 to 50 ohms, and you've got metals going above 0.5 to 1.5 ohms per square. For a square is a square, exactly. So you've got here a length equal to the width. So for instance, a line like this would have more or less 1, 2, 3, 4, 5 squares, more or less. Just to give you an example. So now let's speak about the high complexity of the FinFETs. FinFET is a very complex circuit to do. It's a 3D circuit. Usually planar is just 2D, but doing the 3D at sizes like 16 nanometers or 7 nanometers is very, very complex. So this comes with its perks. As for design, parasitics are complex. You've got multiple parasitics in between the fins. You've got parasitics between the metal that connects the fins and the gate. You've got multiple parasitics. And also you have a long time for extracted simulations. Extracting all of the parasitics that you have on the layout, it's not easy at all. As per the layout, you have a huge amount of rules, really. So this is more or less a graph with the way the rules for layout has been increasing over with the advancement of technologies. I can tell you that design rule manual can have thousands of pages. It's not fun. You have multiple masks per layer. And now onto the project costs of FinFET. You have above $50 to $200K per mask, and development of a project can cost hundreds of millions easily, and takes some years as well. Now let me show you a little bit about the layout. When you're designing a layout with FinFET, you always have a fin boundary. You have the screen on your front, and when looking at your screen, you always have these lines which are the fin boundary, which are always defined. You need to follow those rules. So imagine that you're trying to put a 2-fin transistor down, and these that you see here on blue, it's the fin boundary. So you're trying to place the transistor down, and it needs to be aligned. Wait, sorry. Yeah, it should be aligned. So you're trying to put it down, and it looks more or less like this. You can't put it in the middle. You need to align it with the fins. After this comes the multiple masks per layer. So we start with multi-patterning. What is exactly multi-patterning? So when doing the metal lines in the circuit, as you scale down, you want to also bring the metal lines closer and closer together. But due to quantum effects, quantum uncertainty effects, you can't do it because they will either merge or there will be an open circuit. So the way that the foundries came to overcome this issue was to use multiple masks to do a metal layer. In this case, I'm showing you here double patterning. So first, the foundry will do the red part, and then the blue part. And this way, the lines can be closer together. Also, for the same layer of metal, you have cut metal layers. So what's going to happen after these are put down is that you see these white parts, it's a cut metal layer. And what is going to happen is that this red part is going to be cut off, the blue part cut off. So this will be one part of the circuit, and here you have another. These will be separated, all of them. So just imagine that this is the metal one layer. You have multiple masks to do this. Now onto the potential future of solid-state circuits. What are we expecting for the future? So in terms of transistors, we have nanowires, then complementary FETs, vertical FETs, and then we're going to possibly end up on stacked FETs. I don't know what is going to be the next evolution after this. But I also like to present you something related to quantum mechanics, that we're diving onto realms of that we need to be prepared to use this. So companies are starting to use embedded non-volatile memory with spin transfer torque magnetic RAM. So foundries like TSMC, Global Foundries are coming in 2018, 2019, 2020 with this kind of technology. So let's look onto the transistors. This is a FinFET. Got here the source, drain, gate. We're going to evolve onto this. So the idea is, instead of having the gates on free surfaces of the channel, you have the gate all around the channel. And then we're going to stack them up vertically and horizontally. So this is the beginning of the 3D transistors. Well, FinFET already was, but this is the next step in that evolution. After this, we're going to flip. No, not yet. First of all, we're going just to add the PMOS and the NMOS. We can put PMOS, NMOS, wherever we want. This is called the CFET. Only then, with the vertical FET, is that we're going to flip, and the nanowires will be vertical. And from this, the last step, it's the stacked FETs. So the idea is to continue with Moore's law, so that you can double the amount of transistors that you have in a chip. Now onto the spin transfer torque magnetic RAM. So the idea is to use spin polarized electrons. So you can imagine spin as being an intrinsic property of electrons, and they either have to simplify, they either have spin up or spin down. That's basically it. When you generate current in your circuit, there's always a 50% chance that it's spin up and 50% chance that it's spin down. So this that you see here, it's a ferromagnet with a certain magnetization. When you pass electrons through a ferromagnet with a certain magnetization, the spin of the electrons tends to align with the ferromagnet's orientation. So they end up always all coming with up spin. So the memory cell is a magnetic tunnel junction. You use ferromagnets separated by an insulator as part of the memory cell. So how does this work? Let me explain you. You have a free layer and a fixed layer. So the idea for the free layer is that you can change the magnetization on it. As for the fixed layer, the magnetization stays there for the lifetime of the circuit. The way that you read is through the junction resistance. If the if the ferromagnets have aligned magnetization, then the current passing through will see a small resistance. If they are anti-aligned, the current will see a high resistance. And this is the way that you read a bit if it's 1 or 0, which is stored inside. This can be written using spin polarized current or others. This is the most common method. And this is so important because, or so attractive, one of the main reasons is because a memory cell only requires one transistor. So this that you're seeing here is your memory cell. And when you group all together in the RAM, it looks more or less like this. Now, why is this so attractive? Let's look onto its characteristics. First of all, it's non-volatile. It's you turn off the circuit and it's still there, the bit. It's scalable to below 10 nanometers. So the important thing is to change the magnetization of this ferromagnet. The smaller it is, the smaller the amount of current that you need to pass it through to change the magnetization, and therefore the less amount of power that you consume. Now this is high performance, low power and low cost, and it's so attractive that you've got foundries preparing production for the next years. I've reached the end. I'd like to thank FCT, to thank Técnico, IEEE, CAS, SSC, and Socionext for everything, for support, for planning the seminar. I would like first to thank Professor Jorge Fernandes from Instituto Superior Técnico, who was my master thesis supervisor, and he is a very good teacher. He motivated me a lot to follow on this area. I'd also like to thank Professor Luís Oliveira from FCT Nova, without whom I wouldn't be here. He organized this seminar, helped me a lot. Also Professor Marcelino Santos from Instituto Superior Técnico. I'd like also to thank Professor João Oliveira and Professor João Góes for their sponsorship and their help on producing and advertising this seminar. Last but not least, I'd like to acknowledge all my colleagues at Socionext, which gave me with whom I did some reviews and had some feedback. And we've reached the finish. So thank you all very much for being here. It was a pleasure, and that's all. Okay, so before we advance on to the questions, I just wanted to tell you, everyone, that I'm recording this presentation and putting it on YouTube. The slides will be available for everyone. You can use it, modify it, share it, whatever you feel like. And also I've got some backup slides with an example of the GM over ID and additional information for you to use if you want or you need to. So I'd like then to start the questions. So does anyone have any question?
Actually, I have one question regarding it's more about the economics of this technology itself. So as you mentioned, there's a very high cost associated to this technology, especially regarding the masks, because we need very fine masks with very good resolution, and you need lots of them. So have you talked about $10 million per design, $50 million per design, like in terms of mask, just mask costs?
Well, regarding, unfortunately, I can't disclose any numbers regarding the how much does it cost.
I'm talking about the order of magnitude.
Order of magnitude for, okay, it's so for a tape out, it can be in the order of the millions.
That's what I'm saying. So my question is, what kind of projects or what kind of products justify using this technology? Because I remember a few years ago at ISIS, there was a panel, and basically everyone that was designing RF and socks for RF, they said, well, the identified because they feel it's not economically viable, at least for now, to do
Hmm.
for new design. So my question would be, what kind of products would we expect to see with these technologies?
Okay, so if I understand your question correctly, you're asking why does the RF didn't scale and didn't
No, I
go?
just leave RF as an example. I'm asking what kind of products should we expect?
Yeah.
What class of
So,
products?
so in terms of RF, actually that was one of the things that I was going to say. The RF is not, might not be the best use for FinFETs. Actually, the FinFETs are very good for digital applications and for analog and mixed signal. Also, if you compare for the same overdrive voltage, the pointer bulk technology has a better transition frequency than the FinFETs. So just there, it doesn't, it's not viable to, or not a good idea to follow the costs. Yeah, why, why the need for going deeper is because you start having a better performance, and also these companies that bet on these kind of technologies, the main idea, first of all, is to be a research center, is to be on the cutting edge. That's their main goal, to show that they're in the cutting edge. And they, the projects that they deliver are very are mass products. For instance, in Socionext, we develop optical to electrical converters that are used mostly in data centers, and data centers is something that is booming all around the world. So it has a high demand, therefore the people want to buy Socionext products, I believe, in this sense. I'm not sure this answers your question. Okay, I tried my best. Does anyone else have any question? Go on, sir. I'm sorry, I'm not sure I follow your question. Also, would you mind repeating it a little bit louder?
The quantum tunneling effects of the electrons may cause the saturation of the channels.
Yeah.
Some channels to be a little bit less conductive than what they used to be. Won't that affect the speed of the transistor, since you're stacking more and more channels on the same universe?
So, if I understand your question correctly, you're speaking about the quantum tunneling, the leakage on the gates? Yeah, so as you go advance in nodes, from my research for this seminar, I've noticed that usually the reason why you passed from pointer to FinFET, first of all, is because of the subthreshold leakage, which is the leakage from the drain to the source. But yes, there's also the gate leakage, which is quantum tunneling. As you go down in nodes, that becomes each time more and more preeminent, each time more and more stronger, and actually it's catching for very small nodes. I believe that for 5 or 3 might catch up with the subthreshold leakage. Yeah, that's what I believe, and from the research I've seen. Yeah. Okay. I hope this answers your question. So, does anyone else have any question about the presentation? Go on.
This is a 3D structure, so it might be more sensitive to external forces, being very strong acceleration, for example, dropping one of these sheets. Is that a problem, or it's not really an issue?
You mean dropping a ship, or?
We have a circuit, right?
Yeah.
We have a 3D structure. So we have a fin, which is something that sticks above the wafer. So if you apply lateral force, it might break. Is that an issue or not?
Unfortunately, I don't know the answer to that question. It's something that I haven't researched. I'm not sure that was on the scope of the seminar. So I seriously, I can't give you a reply to the question of what happens when you.
You were fold controls so that you didn't have that much parasites. And those circuits were very sensitive. If you drop them, they would break. So I was wondering if you have a similar problem.
No, as far as I'm concerned, actually these used in computers and wearables. FinFETs are used in. I'm not entirely sure they are already used in phones, but at least in computers I know that they are used. In phones, I believe that they're going to start being used recently or soon. I mean, so I don't believe there is an issue in letting it drop. Okay, so anyone has any further questions? No? Okay, so I'll finish up the presentation, or I believe that's okay. You wanna? Sorry.
So let's Sam continue to solve and we'll, as I said, we'll make available the slides so that they can view them. If they have questions, can they send an email or something? If they have further questions, can they contact me by email?
Yes, you've got, é verdade, sorry, it's true. So if anyone has any questions, if anyone needs or wants to contact me, you have my email at the end of the slides. I believe that as soon as I have the slides and the presentation on YouTube, I'll give to your teachers, they'll give it to you. So if you have any questions, anything, just contact me. I'm open to video calls if you need. Also, just you're here to learn. I'm here to try and give you something new. And that's basically it.